Welcome to the Minor Gastronomy Part Food Science presentation number 4. Today we are going to talk about lipids, and with lipids we mean in fact fats and oils, but there are also some other components that are part of lipids. We will show you later. What are we going to talk about? First of all, what are the differences between fat and oils? What are the differences between animal and plant fats and oils? We will talk about the structure of fats and oils. Fats and oils are composed of two kinds of molecules, one molecule of glycerol, also called glycerin, and three molecules of fatty acids. These fatty acids can be saturated and polyunsaturated. There can be cis and trans fatty acids, and of course the function of fats and oils is primary energy, but also used in structure and storage, also as a taste transmitter. It tenderizes, it has a high boiling point so we can cook. And as you know, maybe we talk a lot about some essential fatty acids like omega-3 and omega-6. I will explain what the differences are. Then we will talk about some reactions. Two very important reactions are oxidation, in which the fat gets rancid. It gives the fat becomes different in color and becomes different in acidity and becomes different in taste. Most of the time, negative aspects. And then, of course, we have the smoking point, which means that at a certain temperature, the fat will start to create vapor, meaning that you are heating the fat at a too high temperature with some negative aspects. Other ones are hydrogenation and saponification. In the old days, we made soap from fats. Then some technical applications. Of course, it's a frying agent, and we can use and have to use emulsions if you want to do something with fat and water. And of course, then some properties will be taken care of. First of all, when looking to the two main types of fat, we have animal fat and we have plant fat. And when we look at animal fat, it's fat that is present in meat, whether this is beef, lamb, pork, poultry, whatever. Also in milk is fat. In the down right corner, you see again the composition of milk. It contains about 4% of fat. From this fat and milk, we make cream, whipped cream. We make butter from that. And of course, the fat is also present in cheese when we make that. When we look at the composition of animal fat, it's about 30 to 60% saturated fat, and it's relatively hard. Let's say it's solid at room temperature. Then plant fat, as we know, we have a lot of kinds of plant fats: palm fat, peanuts fat, nuts fat, soy fat, olive oil, sunflower oil, grapeseed oil, whatever. And these plant fats normally contain a lot of unsaturated fatty acids. And that's also the reason that most of the plant fat are oils. So they are liquid at room temperature. Now, when we look at lipids and we look at how lipids are being composed of different kinds of molecules, we first see that lipids is an overall term of something that has fatty properties. And to the lipids, for example, are counted vitamins or plant pigments and wax types. For example, you have plants that have a small waxy layer on the leaves. That are lipids. Cholesterol is part of the lipids. Phospholipids, these are emulsifiers, are part of the lipids. And then, of course, fats and oils are part of the lipids. And these fats and oils are called in chemistry triglycerides. And the reason for this is that there is one glycerol or glyceride molecule and three fatty acids, triglyceride. So one glycerol molecule and three fatty acid molecules. These fatty acid molecules can be divided into two groups: saturated fatty acids and the unsaturated fatty acids. And then the unsaturated fatty acids can be divided into groups: the monounsaturated fatty acids and the polyunsaturated fatty acids. Unsaturated fatty acids can be either a cis or a trans fatty acid, and this has to do with the structure and the form of the unsaturated bond in the fatty acid. As said, fats and oils are triglycerides, and in the picture on the right you see glycerol, aka glycerin, and three fatty acids. And this is also the reason why we call it a triglyceride. It is one glyceride, glycerol, and three fatty acids, and they react with each other, and then you have, in fact, fat or an oil. The glycerol can react with three fatty acids. It has 3 points of attachment, and a fatty acid has 1 point of attachment, the acid group or the carboxyl group. And the fatty acids have a length of 4 to 35 carbohydrate atoms. So the R group on the far right can be 4 to 35 carbon atoms in length. The glycerol can react with only one fatty acid. It can react with two fatty acids, and it can react with three fatty acids. And when it has reacted with one fatty acid, we call it a monoglyceride. As it reacted with two fatty acids, we call it a diglyceride. And when it has reacted with three fatty acids, we call it a triglyceride. Normally, the fats and oils in our food are triglycerides. The properties of the fat or oil are determined by the composition and consequently the structure and that combination, and also the structure of the individual fatty acids and their mutual position. So a fatty acid can have a long chain or a short chain. There can be 1, 2, or 3 fatty acids present in the fat. They don't have to be all the same fatty acids. And fatty acids, depending on whether it's cis or trans or saturated, have different structures. So there are a lot of possibilities in determining and influencing the property of the fat and oil. In the picture now, you see how the fatty acid has reacted with the glycerol. And you see that in the fat or oil, there are still oxygen atoms present, 6 in fact. But just for the good order, and there is a reason for this that is outside the scope, but we say that fats and oils are not having hydrogen bridges. We say they only have van der Waals. So we just ignore the fact that these 6 oxygen atoms are present in fat or oil. Yeah, that's a rule that we now say. When we look at the structure of fats and oils, then there are in fact three possibilities. We have, of course, the saturated fatty acid, which means there is no double bond in the chain. And then we have the unsaturated or polyunsaturated fatty acids. And when it's unsaturated, there are double bonds present. You can see that in the picture on the left. You see in the blue circle double bonds, the bond between two carbon atoms. And these bonds can either be cis or trans. Now, when a cis unsaturated bond is present, you see that the chain makes a bend or a curve. And at every cis unsaturated bond, there is a curve present. Again, look at the blue circles and you see cis unsaturated bonds and you see that the chain makes a curve. When we look at the trans unsaturated bond, you see that in the red circles that although there is an unsaturated bond present, it has no effect on the structure of the fat and oil. So the trans unsaturated structure is equal to the saturated structure. Only the cis unsaturated structure has a different structure. It has bands in it. And this is very important to understand. We know now that we have fatty acids that have a straight chain, and that's happening with the saturated fatty acids and with the trans unsaturated fatty acids. And we have the cis unsaturated fatty acids that have bands in it. And the consequences of the structure with saturated and trans unsaturated is that these fatty acids can very neatly align to each other and exercise a lot of van der Waals bond interaction forces. So in saturated and trans unsaturated fatty acids that have the same structure, there is a lot of secondary interaction forces. And a lot of secondary interaction forces means that I need more energy to take these chains apart because I have to break more secondary interaction forces. Whereas with cis unsaturated, because of the bands, they cannot align very properly. So there's more a crisscross chaotic system. Compare the cis unsaturated with a box in which you have paper clips. They are not neatly stacked. And compare the saturated and trans unsaturated with a package of unboiled spaghetti. The spaghetti is neatly arranged and the paper clips are chaotic arranged. So with cis, there is less secondary interaction forces because these chains don't neatly stack, so they have less interaction forces. So cis unsaturated fatty acids have less interaction forces and therefore need less energy to break down these secondary interaction forces. And now we can conclude something. The more secondary interaction forces, the more we will have a fat, and the more unsaturated cis, the more it will become an oil. Because an oil is already liquid, so there are not that many interaction forces at a certain temperature left. Keep in mind that I talked about fatty acids, and of course these fatty acids have combined with glycerin, aka glycerol, to a fat or a real oil. And of course there are several combinations possible of fatty acids that combined to the glycerol. Glycerol is here the blue stripe on the right. So you can see that the chain lengths can vary. These are all saturated or unsaturated. In this case, all unsaturated, saturated fatty acids. And you can see that also the chain lengths can differ. Now, we know that when there is a lot of interaction forces, there will be a higher melting point because I have a lot of interaction forces that I have to break down with energy. And if the chains are shorter, there are less interaction forces, so I have less energy need to make it melt. So if I have fats or oils with long fatty acids, they will have a higher melting point than if I have fats or oils with short fatty acid chains. So now we have already two reasons why a certain lipid has a certain melting point. First of all, it's the structure. Cis has bands, less interaction forces. And B, the length of the fatty acids determines also, in fact, the melting point. So if we look to factors that affect the melting point, then we can say a certain lipid has a high melting point if this chain is either saturated or unsaturated, that they are long chains and have the nice zigzag / straight chain and little variation in chain length. And so if you have a fat that is long, unsaturated or saturated, a little variation, then you will have a higher melting point. And then of course, you have a lower melting point when it's unsaturated, cis or short chains, when there are a lot of kinks and bends in it, and much variation in chain length. Now, when we have an oil, for example, olive oil, you will know, because it's liquid, you will know that there is a high probability on polyunsaturated cis bonds, on shorter chains, a lot of kinks and bends, and maybe much variation in chain lengths. So now you know where the phase status, liquid, gas, or solid, is derived from with lipids. When we now look at several kinds of lipids, and we look at the composition of these fats and oils, and then separate in saturated fatty acids, unsaturated fatty acids, and polyunsaturated fatty acids, then you see that in the top you have first of all butter, and then you have meat, and then you get several kinds of plant-based oils and fats. For example, if we look at beef, you see that about 50% is saturated fatty acid and 42% is monounsaturated fatty acid. When you look at pork, you see that 40% is saturated and 45% is in fact monounsaturated, and some 10%, 11% is polyunsaturated. And when we look at chicken, you see that there is about, when we combine those, about 66% mono and polyunsaturated fatty acids. So when you only look at the amount of unsaturated fatty acids, and these are always cis, then chicken is a very good alternative. When we look at butter, you see there's a lot of saturated fatty acids, but also monounsaturated and polyunsaturated. Now, when we now look at coconut oil or palm kernel oil of cocoa butter, what we then see, in fact, is that these contain a high amount of saturated fatty acids. So we also can now say that not all plant lipids contain a little amount of saturated fatty acids. There are that contain a lot. Furthermore, we can also see that we have stick margarine and tub margarine. The stick margarine is in fact a more solid margarine, and the tub margarine is a more softer margarine, where I said stick margarine is a harder margarine. And the tub margarine is softer because it contains far more polyunsaturated fatty acids. So this tub margarine is easier to spread. When we look at the bottom of the table, you see that safflower oil and walnut oil contain a tremendous amount of polyunsaturated and monounsaturated fatty acids combined. So if your goal is to get as much as possible mono and unsaturated fatty acids, then go to the oils. So in general, it can be said that animal fat have equal amounts of saturated and unsaturated fatty acids. Animal fats have fewer polyunsaturated fatty acids than plants. Plant fats, except coconut oil, palm seed oil, and cocoa butter, contain many more unsaturated and polyunsaturated fatty acids, up to 85%. And what we all know, much saturated fat, and especially trans fat, is less good for cardiovascular health than the unsaturated and polyunsaturated fats. Mind you, you need to eat small amounts of saturated fats. Well, here we are looking at the composition of the fat in cow milk. Now, what do we see in this table? In this table, we can identify different kinds of fatty acids. And when we look to the second column from the left, you see a number and a C in front of that, and that determines the amount of carbon atoms in the chain of the fatty acid. So boterzuur, butter acid, has 4 C atoms, and capron acid has 6 C atoms, and then you can go down. And you also see in the second column from the right the amount of this fatty acid present in cow milk. And you see in the right column the melting point. Now, what we see here is that when the molecular mass increases from C4 to C20, arginine acid, you will see that the melting point increases. And this is consistent with what we said. The higher the molecular weight, the higher the melting point. Then we also see that, and that range is of course for the saturated fatty acids. When we look at the bottom, we also see unsaturated fatty acids. A C16 with one unsaturated bond, a C18 with one unsaturated bond, and a C18.2 with two unsaturated bonds. So when there is a 1 behind it, it means only one unsaturated C double bonded C, and when there is a 2, it means you have 2. Or otherwise said, with C16 1 and C18 1, there is only one band in the chain, and with 18 2, there are two bands in the chain. Now we can see what happens with the melting temperature. When we compare the green line, then we compare palmitoleic acid C16 with palmitoleic acid C16-1. And you see that the melting point decreases from 63 degrees centigrade to 0 degrees centigrade. So only that one band decreases the melting temperature from about 60 degrees. When we look at C18, it's the blue line, C18 stearine acid, and we compare that with elaidine acid, then you see that the melting point goes down from 70 to 43 degrees centigrade. Here you see the effect of a longer chain, but also the effect of the band in it. And when we compare the red one, stearine acid, with linoleic acid, linoleic acid has two bands, you see again the decrease from 70 to -5 degrees centigrade. And so when there are bands in it, you see that the melting temperature goes down. Just for information, here you see, we just saw the composition of milk fat, and here you see other kinds of fat. So from beef, from plants, from plant oils, and all the fats are in fact consistent of many different fatty acids. So the composition is not only one fatty acid in a fat or oil, but it's a complex mixture of a lot of different kinds of fatty acids. And this makes it always difficult to predict how such a fat will behave in certain circumstances. What we can say is that due to the fact that a fat contains more than only one fatty acid, is that we don't speak of a melting temperature, but of a melting range. A melting temperature would mean, just like when we have cooking of water, or at 100 degrees centigrade, water cooks. And with fats, when a fat is melting, it will start melting at a certain temperature, and the fatty acids that have the most interaction forces will melt at a higher temperature. So we have a melting range. Well, here we see blue band liquid butter for use in the kitchen. And when we look at the composition, we buy 100 grams of blue band liquid, and we see that we buy in fact 80.82 grams of fat. The fat composition is 8 grams of saturated fatty acids and 52 monounsaturated fatty acids and 22 grams of polyunsaturated fatty acids, composed of omega-3 and omega-6. When we compare this with blue band solid, so the normal butter in the package, you see that the composition is different because there is more saturated fatty acid in it. Instead of 8 grams, we have 44 grams. There is less monounsaturated fatty acids and the same amount of polyunsaturated fatty acids. So due to the fact that there is more saturated fatty acids, it becomes solid. Keep in mind, when you buy blue band solid, you buy 98 grams of butter fat. Whereas with blue band liquid, you buy only 82 grams of butter fat. The other 18% is water. I hope you realize that. Fats and oils show some specific reactions. There are 4, and the first of these reactions that occur with fats and oils is fat or oil oxidation, and that's causing rancidity of the fat or the oil. This fat oxidation most occurs at cis unsaturated fatty acids. So saturated fatty acids and trans fatty acids don't have that problem that much. They also are susceptible to oxidation, but less fast. Now, where do we see this fat oxidation or oil oxidation? For example, when you look at the picture in the top right, you see a package of butter. And people that use butter on their bread will know the phenomenon. When you have taken butter and you put the rest back in the fridge, and the next day you take the butter again, you will see that the butter has 2 different kinds of color. The outside has a more transparent color than the inside. The outside butter has been oxidized by oxygen. And in small proportions, this is not a problem. And the more this happens, the more rancid the butter will become, and the more smelly components will be tasteable. So the thing is that you always have to prevent fats and oils for oxidation. And a very simple way to prevent oxidation is using a packaging material that is closed for oxygen transfer. And when you look, for example, at butter that is in paper, you see that there is an aluminium layer on the paper. And this aluminium layer prevents oxygen from entering into the butter, as long as the aluminium layer is closed. The same we see also with potato chips. When you look at the inside of a potato chip bag, you will see that the color is silver-like. And that's also an aluminium layer between 2 plastic layers, and the aluminium layer is laminated in these plastic layers and is there to prevent oxygen from entering the ship bag. Also, when the ships are being filled, the bag is being flushed with nitrogen to push out the oxygen present, so you have the ships for a longer time in a good condition. So always protect fats and oils for air. That what is happening is shown in the graph on the right side. There is a certain induction period, and you see in the upper exponential line oxygen intake. and you see that the oxygen intake is exponentially increasing. And due to this oxygen intake, volatile components are being made, polymer-like components are being made, peroxide components are being made, and aldehyde components are being made. And at a certain time, we smell rancidity. And when that happens, the reaction will go faster and faster and faster. So once starting, you have to scrape away a lot, otherwise it will continue. If you have oil in bottles and you have big bottles, you have to use the bottles as fast as possible. Don't have bottles standing on the shelf for months after months, because the oil will get rancid. Now, what is influencing the oxidation rate? First of all, the composition of the fatty acids present. And polyunsaturated cis fatty acids are very sensitive to oxidation. Also, the presence of free fatty acids. They are not bonded to the glycerol, and they are even more sensitive than the bonded unsaturated cis fatty acids. Of course, the oxygen concentration. The more oxygen is present, the more the reaction can proceed. And of course, the temperature. The higher the temperature, the faster a reaction will go, so also the oxidation reaction. The surface that is in contact with air, for butter, it's quite a small surface, but if you would look at chips, in the bag, there's a lot of surface. So surface is very important. Then you also have the water activity, and there is an optimum for the water activity and the oxidation of. There's a minimum of the oxidation for in relationship to water activity. Then you have the presence of material that will enhance the reaction, pro-oxidants, and especially some metals, copper and iron. And of course, light will also increase. And that's the reason why we keep the butter in the fridge. A way of preventing the oxidation is that we add antioxidants. Now you can see here two very simple reactions. And what I have to tell about this reaction is that when the double bond is being broken, the molecules that are left have both one electron that is not shared with another atom. And such an electron is called a radical. And the radical is being represented here by the dot in the equation. So you have ROO dot plus AOH gives ROOH plus AO dot. Now, the dot is in fact the radical. Now, and the ROO dot is in fact the broken up fatty acid. And the AOH is the antioxidant. So AO is antioxidant, and it has a H attached to it. And what you see is that the H is being transferred to the fatty acid, becoming a normal molecule, and the antioxidant has become a radical. It has the dot. So that's now the radical, that's where the radical is. And the antioxidants have not a problem with this free radical. They will not react with that free radical to other products, whereas the fatty acid that has the radical will react with other fatty acids. So in this way, the reactivity is first transferred to the antioxidant, and B, the antioxidant will not react further. And this is how antioxidants function. And below you see some antioxidants. So vitamin D and vitamin E and vitamin C are all antioxidants. And look at the question that is on the left at the bottom. If you look at these molecules, which one is best dissolved in water? You should be able to answer this question because of the first presentation. The second reaction with fat and oils is that we add water and acid to the fat and oil. And what then happens is that we break up the glycerol and the fatty acids from each other. So we get glycerol and we get the fatty acids. In this equation, you see that stearic acid is being formed. Both have use in other products. For example, the stearic acid is used as candle fat. Also, palmitic acid, the fatty acid version, is in fact used for making candles. The glycerol can be used, for example, in cosmetics. In reaction 2, we added water and acid to the fat and oil. In this reaction number 3, we add strong bases. So we go to materials that have a pH of 10 to 14. So the opposite of acidity. And when you look at this reaction, you see again that glycerol is being made, and also the fatty acids are separated again from the glycerol. But because we now have used sodium hydroxide as a solvent, we now have made an ion bond sodium fatty acid. You can see sodium, oxygen, and then the rest of the fatty acid. And that's an ion bond. And these fatty acids are used as a soap because they act like a detergent. So when you now take the soap Palmolive, you know that Palmolive is made from olive oil and palm oil, and that they have degraded the oil into the soaps and glycerol. Now, the glycerol, as said, is used as an agent in cosmetics, as a moisture retaining agent. It's sweet, it retains water too. And when you add nitric acid, you have nitroglycerin, an explosive. In food, it's used as a sweetener, but only at certain in certain products. In the old days, some acidic tasting wines in, I think it was Austria, but I'm not sure, it could be Germany too. They added glycerol to make it more sweet, which was forbidden. So you don't do that. So when we make from a fat or an oil, by using sodium hydroxide, a very strong base, we make the soaps. Then these soaps act like a cleaning agent, and they can act like an emulsifier. The last reaction that concerns fats and oils is the reaction that is being determined by the smoke point. And what happens is that at a certain high temperature, the fat and oil will disintegrate by themselves. And the temperature at what this disintegration happens is called the smoke point. And how can we see the smoke point? Well, look at the vapors coming from the fat or oil, the molten fat or oil. And when these are blue vapors, you know that you have you have more than reached the smoke point. So the smoke point has already been surpassed. When fat is smoking, it's first of all far too hot. B, it disintegrates, and then components are being made that are not that good for us as humans, and they have an unpleasant smell, and can be toxic. So change the fat in time and never use a too high temperature. Due to this disintegration, the fat will become more and more acidic. So you can check also by measuring the pH, and most of the time this can be done with dipsticks. You can just measure the pH, and it is below a certain level, you know that you have to change the oil or fat. Now, the smoke point or the height of the smoke point depends on certain factors. First of all, the content of free fatty acids. So the less free fatty acids, the more stable the fat, the higher the smoke point. Fresh fat has a higher smoke point than old fat, because old fat has already degraded for some time. Refined fat, so very pure fat, has a higher smoke point than unrefined fat. And the presence of other components in the fat decrease, in fact, the smoke point. As I said, I was going to talk about why do we clarify butter. You see the process here in 4 pictures. You heat up the real butter, then you see some clouds of protein occurring in the liquid oil. You separate the solid part from the liquid part, so the proteins and salts are being removed, and then you have more pure real butter, which has a more stable character and which has a higher smoking point. So every kind of butter in which we have mixed whatever has a low smoke point. Then there is something that is very important. Also, we have the oil that has a certain smoking point. And when you start, for example, using fat that has been too old or has had too hot temperatures above the smoking point, then you have old frying fat. And this may give rise, when you start using the fat for making French fries or whatever, that nitrosamines can be formed, and these are not healthy. That's also the reason that in the last 10-15 years, the temperature for frying fries has decreased from about 200 degrees to now 170 degrees centigrade, to prevent this molecule from being formed, because it's not good for your health. So this is also the reason that our French fries are not that brown anymore as in the old days. So when we now look at blue band liquid again, we know that there is 18% water in there, and we look now to the composition in the square, the lower square. You see that these oils and fats are derived from rapeseed, sunflower, in different compositions, and some is a little bit hardened. And then water is added, 18%. Keep in mind that that's the gain of Unilever. This is where they earn a lot of money. With 18% of water, that doesn't cost anything. And they add salt. Why the hell do they add salt? Then they, because they have water now in it, the oil would be floating on the water. And when you squeeze the liquid butter in the end, you would get water, and then every customer would know, hey, there is water in here. That's not correct. So to mix the water with the oil, they need emulsifiers, and in this case, sunflower lecithin and soy lecithin. Because they use water, the taste is different, and to get again a good taste, they add an acidic component, in this case lemon acid, and they add aroma, and they add coloring agents. And to make it more healthy, they add vitamins A, D, and E. Well, you can expect now this is a very complex composition, that the smoke point of this kind of butter is far more lower than the smoke point of a very pure butter. I talked to you in the previous slides about emulsions and emulsifiers. So I have to explain to you what an emulsion is and what an emulsifier is. Well, we all know that water and fat or oil don't mix. And the reason for that is that fats and oil are apolar, don't have oxygen and nitrogen, and water is polar. So water cannot form van der Waals bond with fats or opposite. They don't mix. And because they don't mix, and that you can see in the right bottom picture, you see that the oil after a certain time will float upon the water. And this is something that we don't want in the creative cooking process. So we have to do something. So we are going to try to make an emulsion. And in fact, an emulsion is in fact a composition of two liquids that ordinarily don't mix. So if I would mix, let's say, sunflower oil or olive oil with water, then they will separate. When I would mix with very much force, the small droplets of the olive oil in the water will become so small that the mixing goes a little bit better, and that the time for unmixing is longer. Yes. So an emulsion is a combination of mixed liquids that normally do not mix. Because of the repelling, because of the differences in secondary interaction forces, a separation in time will take place. Now, when we look at emulsions, then you can say that an emulsion is one liquid very neatly dissolved, present as droplets in the other emulsion, in the other liquid. And the material that is the droplet is called the dispersed medium. And the medium that is in which the droplets are dispersed is called the continuous medium. So the droplets is always the dispersed medium, and the rest is the continuous medium. So there is already one rule that we can say, that is, the smaller the dispersed phase is distributed in the continuous phase, the more stable the emulsion will be, but in time it will show phase separation. The fat or oil will start to float on the water. So when you have to make a dish that will be eaten within several minutes, then just by stirring you get a good emulsion. If it will take more time, you have to find a way to make it stable for a longer time. How can we make an emulsion stable for a longer time? Well, there are two ways of doing this. First, you can add an emulsifier. Most of the time, these are proteins or lecithin or smaller fatty acids. And then you can add a stabilizer. I will come to that later. So, looking at the picture in part A, you see the non-mixed oil and water. In part B, you see that we have stirred, and it is in fact an emulsion. But in part C, you see after a certain time, this emulsion will separate again. Now, and when we add an emulsifier, for example, casein, a protein of milk, you will see that the droplets stay in the continuous phase and don't show phase separation. This is how an emulsifier functions. Now, and why does an emulsifier do this? This is possible because the emulsifier has one side in its structure that is polar and has the other side that is apolar. So with the apolar side, it can form van der Waals bridges with the oil, and with the polar side of its molecule, it can form hydrogen bridges. And in this way, it attaches to the oil and the water, so the oil and the water cannot attach to themselves. And this way you have a stable emulsion. We can obtain a quite stable emulsion if we add an emulsifier. And if we make the dispersed phase, let's say it's oil, as small droplets as possible, we get a very stable emulsion. There is a further advantage when we have very small droplets. Suppose that in the oil you have very nice color components or taste components or smell components or aromas. The finer these droplets are, the more taste will be released when you eat these very small droplets, this very good dispersion. There is another way to make even a very, very, very stable emulsion, and that's called a stabilized emulsion, and therefore we need a stabilizer. So how do we make a stabilized stable emulsion? And then we start using those products with which we can make a very nice mesh network-like structure. And you have learned that we can make mesh-like or net-like structures by using, for example, gelatin or globular proteins or starches. So in this picture, you see the three ways of making an emulsion. On the left, you see oil drops in water, and the smaller these oil drops, then we have an emulsion, but it's unstable. In the middle part, we have added an emulsifier. And you can see now small dots on the oil droplets. This is the emulsifier. And the emulsifier on the outside has its polar part, and on the inside of the droplet is the apolar part. And then you have a stable emulsion. And on the right side, you see we have stabilized the stable emulsion by adding the network, the white mesh network. In this case, starches or proteins. Now, the stable emulsion is stable for a very, very long time. So if you need for a very long time a stable emulsion, you have to stabilize it. Here you see how mayonnaise is being made. Keep in mind that mayonnaise is 80% of, let's say, oil and 20% of water vinegar. And the oil is the dispersed phase, not the water, the oil. So the oil is present as very small droplets in the continuous phase of water. So there is only a very tiny water layer around each droplet. If you want to make mayonnaise, you have the water and egg yolk present in your beaker, and then slowly and good stirring you add oil, and you have to do this very slowly so you break down the droplets to the right size, and when you continue you will have mayonnaise. You can add spices, you can add vinegar, and of course you can add starch or egg white to make it stabilized. Here you see, in fact, pictures of the small oil droplets in the water, and in the picture right top you see in fact the water droplets, the oil droplets, the darker parts, and the water, the light parts in the middle, and on the surface of the oil droplets you see let's say small black dots, and that is the emulsifier. And this is what happens just due to the fact that we can combine with emulsifiers repelling liquids having either van der Waals secondary interaction forces or hydrogen bridge secondary interaction forces. Same applies for vinaigrette. It's also 80% oil and 20% vinegar, but no, we don't stir that much. We mix all together, and there's no emulsifier added. You will see that this is also not that stable, but that's not the idea for a vinaigrette. Well, here you can see again where the information came from. Of course, in McGee, as said, there is a Dutch and an English version. If you want to know for the Dutch version which pages, then look in the module book. Good luck.